Voltage dip. Distributed generator do not result in any significant direct increase in the number of voltage dip. The only possible impact is that voltage dip due to connection of generator to the grid. This is a concern only for generation with rotating machine interface, and even in this case typically a soft starting is used to limit this voltage drop. The presence of distributed generation, however, will impact the number of dips in the several indirect way. So let us see that what are the impacts that are done in a indirect way. Distributed generation connected to distribution system with locally strengthened the grid, so which will result in the decrease of number of dips which are experienced by local customers. We will consider this impact in more detail. Looking at a synchronous machine, the damping effect of induction generator on a unbalanced dip, it is treated here. The replacement of large conventional power station distributed generation will weaken the transmission grid, so which will increase of number of voltage dips which are experienced by customers. So this has been studied by UK transmission system. It is estimated to 20% of distributed generation. So we will for no customers which results in doubling or more number of voltage dips. As the number of dips will vary so much more from year to year due to the lack of any guidance on what are the acceptable levels. So this is seen as a moderate increase in nowadays. So and also the large penetration of distributed generation will requires the enforcement of power system in the form of new cables or overhead line. Especially the integration of large wind park in the subtransmission and transmission system is reported to require a significant amount of a new line. This line will also result in more voltage dip for customers which are connected to close to these lines. So this may especially impact large industrial customers that have traditionally been more sensitive to this voltage dip. So the authors are in this book are not aware of any such studies which are impacting this penetration of distribution generation. Weakening of transmission system may also result in a longer fault clearing time. Thus, a lower voltage dips, the distance protection and differential protection are not much impacted by this fault level over a broad range of fault level. But overcurrent protection sometimes used in subtransmission system may be impacted. After the fault clearing, the rotating machine takes a large reactive power in weak system, so this will pull down the voltage after the fault, and which also result in longer voltage dips. So here we enter a real name transmission system, so where impact very strongly depends upon our system. So here the power electronic converter which may distribute in which many distributed generators are equipped, so can be used to maintain a voltage for the local load. So here the two different approaches are discussed, like temporary islanding operation of the generator with a local load, and the injection of reactive power during the dip while remaining connected to the grid. So more detail about these different algorithms are discussed under this voltage dip topic. So moving on. Synchronous machine balanced dip. Okay. Consider a simplified system which is shown in the figure. So this is the figure I am talking with respect to. So synchronous generator SM is connected to a medium voltage bus MV. Here you can see medium voltage bus MV. Synchronous generator is connected to medium voltage MV to the secondary side of HV MV transformer. So during a fault, the synchronous machine can be modeled as a voltage ounce behind the impedance. If we further neglect that load impedance, so on the voltage which influence the synchronous machine on a voltage at a transmission level, we get a model on right to calculate this voltage which is experienced by our end customers. The residual voltage is given by UMV. Here you can see this is the residual voltage UMV is equals to Z gen, impedance of generator to the impedance of generator to the impedance of transformer, UHV plus again impedance of the transformer to the combination of product of sum of impedance of generator or transformer. So if we further assume that a back EMF Egen of synchronous machine is equals to 1 per unit, so we get the following expression, that is 1 minus this one 1 minus UMV is equals to Zgen divided by Zgen plus ZTR 1 minus UHV. Okay. So the voltage experienced by end customer in this case is no generator connected at a medium voltage which is equals to UHV. Also the reduction in the voltage drop is related to the impedance ratio between the transformer and the synchronous generator. So here N dip is equals to N50 minus ratio of V to the V minus 1, where N50 depends upon the system configuration at a fault frequency. So this expression has to be divided from theoretical model and has been confirmed by both simulations and measurements. The number of diff below UMV at the medium voltage bus is equals to number of dips below UHV at a high voltage bus. With UMV and UHV, so this can be related. The remaining voltage due to one specific fault is not direct relevance to a customer. The power quality which is experienced by customers is instead qualified as the number of voltage dip over a long period with a residual voltage below a certain threshold voltage. So this gives an information to the customers on the number of times per year that is the device or the process is experienced to trip. To estimate the impact of this distributed generation on the number of dips experienced by end customers, so we use the simplified relationship between the number of dips and the residual voltage. 1 minus UM is equals to Zgen divided by Zgen plus ZTR into the product of 1 minus UHV. Inverting this expression, which leads to the following expression for the measurement of dips which are experienced by our end customers, where NMV of V is equals to N50 minus V power 1 divided by V power 1 minus 1. So in the latter cases, this expression interesting because the ratio ZTR divided by Zgen can be easily linked to a percentage of distributed generation. So here let ZTR be the transformer impedance in per unit on the base which is equals to the transformer rating, that is STR and Zgen be a per unit generator. The per unit generator impedance on the base which is equals to generating rating, that is Sgen. So this is this will result in the one more equation, that is ZTR divided by Zgen. Here you can see that is equals to ZTR divided by Zgen into pi of dg. by combining the last two expression, which will result in the following expression for number of dips below the threshold. So V at a medium voltage bus is given by NMV is equals to N50 minus V bar divided by V bar minus 1. So with V dash is equals to V minus ZTR divided by Zgen into 1 minus V pi dg. So here the consequence of the second term is that dip threshold at a medium voltage, which is correspond to low dip threshold at a high voltage, thus a lower dip frequency. So the bigger the second term, there will be more in reduction in the dip frequency. In increasing the amount of distributed generation with this synchronous machine interface, will leads into the increased reduction of voltage dip frequency. Moving on. So this is about synchronous machine balanced voltage dip. So let us see the synchronous machine unbalanced voltage dip. A simplified theoretical model to describe the impact of rotating machine on voltage dip. Although the model has been developed for induction motor, it is equally valid for induction and synchronous generator. So the relative reduction in the dip frequency is due to the increase in the amount of distributed generation with a synchronous machine interface SA or FI, that is 40 a solid line, SAFRI for 70, that is dashed line, SARIF 80 for dotted line, SA or FI 85 for this dashed line. So the impact on the positive and negative sequence impedance is treated separately. Here we will apply this model to distribution system with synchronous or induction generator. The basic model is shown in the figure. This is considered this basic model. So the rotating machine, so it may be induction machine or an synchronous machine, is modeled as an voltage source. Behind the reactance for positive sequence and positive sequence voltage, and as a constant impedance for negative sequence voltage. So this model has been confirmed by both measurement and simulations. For synchronous generator, the voltage EM of T is constant. So this voltage depends upon reactive power exchange between the generator and grid. So the more reactive power produced by the generator has an highest magnitude of this. Considering the first synchronous machine case, a voltage dip occurs at a point of common coupling with a positive sequence, that is U of 1p, and a negative sequence at voltage U2 of p. The positive sequence voltage close to generator is obtained from U1 of M is equals to Zm divided by Zt plus Zm into U1 of P plus Zm divided by Zt plus Zm into the product of this Em. So in the negative sequence voltage close to generator is equal to U2 of M, that is Zm divided by Zt of M into U2 of P. A complete characterization of unbalanced voltage dip. The method distinguished between the unbalanced dip of these two basic type, which is referred as C and D type, which uses characteristics, two characteristics quantity for the severity of dips, that is the characteristics voltage V, so called PN factor. The characteristics, another one is the characteristics voltage, that is generalization of residual voltage for a single phase event. The PN factor is a rather complicated concept where difference between the characteristics voltage and PN factor qualifies the amount of unbalance in the voltage. both the characteristics voltage and PN factor are complex numbers. The basic classification has recently been taken over international working group, where the type D is referred to be a type 1 and type C is referred as type 2. A type C dip constitute a voltage drop in magnitude for 2 phase to neutral voltage. The following expression holds good for 3 phase to neutral voltage in case of such voltage dip. So UA is equals to F, UB is equals to minus half V minus half JV root 3, UC is equals to minus half V plus half JV root 3. Type D or type 1 voltage dip constitute to the drop in the magnitude for phase to neutral voltage with the following expression for phase to neutral voltage, that is U A is equals to V, UB is equals to half V plus half V minus half JF into root 3, UC is equals to minus half V plus half into JF root 3. So these are the above one is for type C and the below one is for the type D, so voltage dip. A transmission and sub-transmission level, the PN factor is very close to pre-fault for positive sequence voltage for a dip due to the single phase and phase-to-phase fault. Whenever it is close to load, the PN factor becomes smaller, especially due to the impact of induction motor load. Here we assume that PN factor to be equal to be pre-fault voltage at PCC, and will calculate the impact of distributed generation on both the characteristics voltage and PN factor. To illustrate the impact, so of the synchronous generator, an unbalanced voltage dip is considered. So this is the unbalanced voltage dip. A 10 megawatt synchronous generator here connected to a medium voltage network. The reactance of the machine, including the generator transformer, is 25%. The HV bar MV transformer is rated at 40 MVA with 20% impedance. The positive and negative sequence voltage in this medium voltage network for a voltage dip originating at higher voltage level are shown in this graph. The voltage dip at PCC is calculated with F is equals to 1 per unit. The positive and negative sequence voltage are calculated using the standard expressions. The transfer from HV to MV is calculated by the set of equations which we discussed in our previous slides. So the positive and negative sequence voltage are shown in this figure, this graph, as the function of characteristics voltage at a common point of coupling. Because of presence of synchronous machine, the positive sequence voltage will increase in the magnitude and negative sequence voltage will reduce in magnitude. The calculated positive sequence voltage at a medium voltage bus have to be used in our calculations, and the phase to neutral voltage which are shown in the above graph for C type. So with the presence of synchronous machine, the voltage drop in the machine is experienced in a distribution network, so will become less. So distributed generation thus improves the voltage quality of the customers. For type D dips, combining the above the equations will give the relationship between the lowest phase to neutral voltage at PCC and in distribution network.